Okay, welcome to this next lecture. We're still talking about linear DAEs with constant coefficients, like we have been doing this for numbers of lectures. So this is another continuation. Today, or maybe last lecture, we learned what if EA regular, what this means, and this in particular meant that that such a pair is equivalent to such a very special pair, J and identity here, which, as we showed, will decouple the DAE very nicely. And then so this will turn into the DAE into an ODE and into a very particular, we had this x2 plus f, and so that's what we will consider today. And well, since ODE is easy, then we will show that this has a solution. So we will here, you see, EA regular. So we will see that there's a solution to the DAE with this matrix pair. Then we will have a solution formula, particularly for here. And then we will have a little look what is if EA is not regular. What can we say about solution? Okay, but now let's start with the lecture. So last week we said EA is regular. Then well, EA like this DAE is basically equivalent to x1 dot is j of x1 plus f1, and this n matrix x2 dot is x2 plus f2. And we will, so this is this very special DAE. I call this the N DAE. Don't care about this. And as I said, this has the unique solution because it's an ODE and it's even in Jordan form, so the solution is easy to write down. And there's these other really DAE with this particular n matrix, and we had this n was a nilpotent matrix, which in particular meant that, if you recall the definition, that there is an index nu such that n nu plus 1 is 0, whereas n nu is not 0. So then the n is a nilpotent matrix. We had a definition on that. Let me just see whether I'm yeah. Okay, and now we define the what basically is a bit better definition for this nu, because this actually defines an index, as we will see. So we will start with defining the index of nilpotency, and this says that let n in the square matrices, we need to take the square of n and the third power, so it needs to be a square matrix. So let n be a square matrix, be nilpotent, then the smallest integer nu such that n to the nu plus 1 is 0 is called the index of nilpotency. Okay, why this it might be interesting to have such kind of well, this particular definition. This somehow all fixes this new, because well, it's also a bit inside here with this n to the new being not equal to 0. Oh, but with taking to be this the smallest integer, that this fixes this new, because if nu plus 1 is 0, then of course nu plus 2 is 0, so you can go forever and you will have a 0, and like the smallest one. That's the important thing. So that new, so that nu plus 1 is 0. This is called the index of nilpotency. Okay, and I was already wrong here. Well, here, that's important. Like the sorry. I'm really sorry for having messed this up. So we look for nu. I wrote the nu plus 1 here, but it's in fact the nu for which it is 0, not the nu plus 1. So here we should write this like this. Nu is 0 and nu minus 1 is not 0. And yeah, then the smallest integer such that n to the new is 0. And well, we can go back to this example if like this matrix that we have, that the new is 2, because 0, 0, 1 squared is the 0 matrix. And then again this convention 0, 0, 0, 0, there the new is 1, because well, by that's now a convention. The 0 matrix to the power 0 is the identity. Okay, yeah. So this is the index of nilpotency. And if we have this index of nilpotency defined, we can now come up with a solution formula for this particular DAE, for this NDAE. And this goes, so now we consider this particular NDAE. Here I somehow dropped this index x2, f2, because we have the particular case and no need to spend too much time on these indices. So assume we have such a DAE to solve, and x dot is nx plus f, with f being in C nu, meaning it's nu times differentiable on this time interval that we consider. Then this lemma stays. Then the unique solution is given as x of t is minus the sum k goes from 0 to nu minus 1, and to the k f and the kth derivative. So this parenthesis k in the power means the kth derivative or at time t. So this gives you the solution to that. I will prove this on the next slides, and I think then it becomes more clear what all this means here. But here's the solution representation. Okay, and maybe also certainly important is that this has a unique solution. Yeah. Okay. no need to distract. Okay, unique solution is given in this form. There are many ways to prove this. One can, for example, have this particular, sorry, somehow I'm not in the flow. Jordan form of n, which looked like 0, 0, 0, for example. And for these particular n, one can just write down the solution and see that it is of this type. And then one has to do some induction because, well, there can be more blocks to that. And then, well, so this is one particular way of proving this. Another one, this is how it's done in the Kunkel and Merman book. You can consider the operator n times d by dt. Well, and show that I minus n d dt with a minus 1 exists. Okay, you can do that, but I don't like this particular proof too much because, well, actually you should have some more arguments than that other than just the formal that is used in the book. Yeah, there's a direct way to show this. Direct way, and that's how we are going to do this. And the direct way looks like we start with n x dot as x plus f. Then what we can do is, let's take another color. Oh, I wanted to start the other way around, so nothing changed. We say that x is nx dot minus f. So this really makes no difference. So here's nx dot is x plus f. We put x there and nx there. So we get this. And then what we can do, well, write this down once more. Nx dot minus f. Then we can multiply by an n. So n, then we get an n squared here, and we get an n here. Okay, then we can differentiate with respect to time. Let's take another color for that. Some out of colors. Could be a visible color. And then we differentiate. So we can differentiate all that. So nx dot, of course we have to differentiate here as well. And then also here. So we differentiate everything with respect to time. So with that colorful thing, yet another color, we have that nx dot is equal to that, and what we do here is replacing this nx dot with all that is there. So that will give us that this is actually n squared x double dot, so second time derivative, minus nf dot minus f. Okay, and then we do the same again. So same equation here, and x dot is n squared second derivative minus n f first derivative. We multiply by n once, so n squared, n to the 3, n squared, and differentiate x3 second derivative. And then we replace here. we replace this x, this n squared x double dot by what we have here. Okay, so this is actually basically the same as n to the 3 x double dot minus n squared f, and we have to keep this here, minus nf dot minus f. And this we do on and on and on till we come to n nu to the minus 1 okay. N to the minus 1 nu, and here we have nu to the first derivative is the same as n to the nu x, and the nth derivative minus n to the nu minus 1 times, sorry, that's not consistent, n to the nu minus 1 f and then nu minus first derivative. Okay, and then we see that this here is 0 because nu was the index of nilpotency. Okay, yeah, I have to add this to the theorem in a second. So n is the index of nilpotency, meaning this part is 0. 0 because n to the nu is 0. Okay, and so like as we always replace this term that remained here with what is here, then the last term that we will add is this nu to the minus 1. So we do this on, and then we get here minus n nu to the minus 1 f nu to the minus 1 minus everything that was in between n f dot minus f, and this is exactly minus the sum k goes from 0 to n to nu to the minus 1 n to the k f in the kth derivative. That's the proof. So here is x is the same as all this. Well, that's the proof. No one might argue that there might be another one, but you can either say that's constructive, so you took the solution and showed that it looks like that, so this, that's straightforward constructive way. But if you're not sure about that, then take x1 sorry, take two solutions, u and v, show that u is equal to v by same approach. Okay, and well, that's a proof, and I have to fulfill, complete the theorem where nu is the index of nilpotency of n. Okay. Yeah, and here, let me highlight this once more. So here, that's the theory. for this particular DAE, with n being nilpotent, with of index new, the unique solution is given as, well, in this form, just depending on derivatives of the right hand side. And what you here already see is that the right hand side needs to be differentiable, and actually, well, here it goes to nu to the minus 1, so you may think that nu to the minus 1 may be enough, but in order to be a solution, one needs to be able to take another time derivative of here, and this should also be defined, so we actually need the derivatives up to the order of nu. Okay, and that's the proof to that. Some reflection on the nu. What did I want to have here? Well, let's see. It defines the necessary smoothness of the solution of the right hand side. Oh, that's basically it. So you say, and it also defines one of these indices that I mentioned, an index. And that's basically this definition. Given a matrix pair EA, and CNN, EA regular, then the index of nilpotency of the associated canonical form of the index of nilpotency of n of the associated canonical form is called the index of the matrix pair EA. We write nu as index of EA. Okay, so maybe a little reminder, this canonical form, so that you have it together, means that this is equivalent to En J identity, and here the important, this is the n that defines the index. Now, in order to have this, well, if you write down a definition, you can always do this, of course, but what is most important is that it's a definition, so it's not ambiguous. It is, and the term for that is well defined, meaning, well, there will be only one possible number for the for the index. And this is now in this following lemma, saying that this index nu is well defined for any such regular matrix pair EA. Meaning, here's the lemma. Suppose that EA regular, forgot this. So suppose that there is a regular matrix pair that has canonical form EA strongly equivalent to En Ji, but now n and j are different for, say, for 2. We show that if 2 are different and they're similar, then this holds for all, but well, important is that if there are 2 different canonical forms, that are associated with this EA, then this is the important part here. Then the indices of nilpotency for N1 and N2, they coincide. And another thing that is also necessary, that D1 and D2, which is the dimension of here, of these blocks, they are the same. And this also implies that the N1 and N2, they have different sizes, but they have the same index of nilpotency. Oh, no, they have the same size. That's necessary. They might differ. You can find transformations where N1 is in fact different from N2, because we only said that it should be a nilpotent matrix. We didn't specify more. Also, like these J's, they can be different. We say there's no natural, particular for complex numbers, there is no natural ordering that these eigenvalues should come first and these come second. So they might in fact be different, J1 and J2, but what is important is that the size of these Ji, they coincide. So they are the Ji's are of the same size, and the index of nilpotency for N1 and N2, that they coincide. Well, let's start with the proof. And I include this proof because this also shows a bit how to calculate with these matrix pairs and these transformations. First thing we need to show, first we show D1 is equal to D2, which means N1, N2, J1, J2 each have the same size, same size. So we show D1 is the same as D2. How do we do that? So say EA is similar to let's write it here. Lambda E minus A is similar to lambda identity minus J1 lambda N minus identity and N1, and similar to lambda I minus J2 lambda N2 minus identity. This gives us that that the determinant of lambda E lambda E minus A is the determinant. So if you have such a block matrix, then the determinant is the product of the determinants of the blocks. So this will be lambda I J1 times the determinant of lambda N minus 1 minus I. Now we recall that N1, it looks like, most importantly, it has zeros on the diagonal. That we had in the proofs before, that if a matrix is nilpotent, then it's upper triangular with zeros on the diagonal. So this N1 matrix will look like that. this means that lambda n 1 minus identity determinant of that is only the 1 to the minus only the no, it's just the ones, because the determinant of a matrix is the product of the, so if product of the eigenvalues, well, not the same. sorry. Well, this sorry. So I'm reading. 1%. Okay, sorry. Okay. Lambda determinant of this matrix is, here we have ones with a minus, minus 1, minus 1, minus 1, minus 1. And then we have lambda times something, lambda times something, lambda times something. Doesn't matter. So on the main diagonal there will be this minus identity. And this is then minus 1 to the product and minus d1, meaning, well, that's the minus 1 times the size of this identity. The block of the size of j1 is d1, then what remains here is n minus the d1, and that gives us, use more colors, this gives us this determinant here. So here we will have minus 1 and the d1, which is this part, times times the determinant of this part, lambda I minus j1. And this is by a previous lemma because of similarity. This is constant times determinant of lambda I minus j2. Yeah, okay, once more. So for this determinant we can compute as determinant of this part, which determinant of this part, which is minus 1 of this vector. So this is just a factor to that, and then it remains to the determinant of this part. Now by similarity, when we were showing that regularity is invariant under similarity transformations, we found that the determinants of that this characteristic polynomial of two equivalent matrices, they only differ by a constant factor. So here that's a constant factor. This is also a constant factor, so we put this into this constant factor, and well, what remains, and this is the part of that's the J2 part. So yeah, this was the J1 part, and of course if we do this for J2 we come to the same conclusion but with the J2 here. meaning these polynomials, they are equivalent up to a constant factor. This is a constant factor 2. Well, and this in particular means we continue here. This particular means that that the degree of determinant, so this gives a polynomial, should be the same degree as of this polynomial, lambda e minus j1. And this in particular implies that, well, d1 must be the same as d2. If they, okay, back once more. Here with all these calculations we found out that the determinant of lambda I minus j1 should be a constant factor times the determinant of lambda 1 minus j2. Okay. If two polynomials only differ by a constant factor, this means that the degree of the polynomials are the same, and the degree is like the largest power that is in the polynomials. And they can only be the same if if the d1 is the same as the d2. If they have different size, the polynomials will have different degree, and this cannot be. So they have to be the same size, and then they can have the same degree, and then this can hold. No continued. Next thing would be to show that that in fact the indices of nilpotency, that they coincide. I think I will, now since it's technical, I will write this down in the lecture notes, and then maybe we can talk about that in the next live session. I would rather like to use the final time to discuss with you what are now really the outcomes out of all these computations we did so far. And for that we summarize everything in a single theorem. So last thing for today, theorem, previous last thing, there will be one more thing. Actually it's all proven already. So let consider now the pair EA of square matrices that are regular, and P and Q are regular metrics, so that we can consider the actual DAE. This is the actual DAE with an initial condition. And with all what we did before, we take P and Q and transform this initial DAE into this transformed ODE. That looks like that. By means of that, and what's important, this A tilde, oh yes, it's too late today, so there of course is always an E, otherwise it wouldn't be a DAE. E tilde, X tilde, so that DAE is transferred into the DAE by means of P and Q. And we assume that E tilde, A tilde is in this Weierstrass canonical form, which in particular means that E tilde is P E Q is given as identity n matrix, A tilde is P A Q is given as J times identity matrix, F tilde is P F. Okay, what is important too? X tilde, so we say that they relate like the x is basically the q times x tilde, meaning that x tilde is q to the minus 1 x, which we will write also as x1 tilde x2 tilde. And then in particular we will have that x tilde of 0 is q to the minus 1, x of 0 is q to the minus 1 x0, which then should be the initial value for the transform system. And this also we will split this according to that. This should be then x tilde 0, 1 and x tilde 0, 2. Okay, here we have it all on one slide. How these transformations are realized. So, and yeah. Okay, let me repeat this once more. Consider EA square matrices regular and P and Q transformation matrices regular, and we transform the actual DAE EX dot AX plus F with initial value into the transformed DAE for X tilde, with now also initial condition X tilde. And then, with all what we did so far, we can say that the DAE, so this part here, is solvable. Why? Well, because wait, here. Because by this transformation we get into these two parts of the DAE. Here we already said that this is not a problem, this is solvable, and for that we now showed that there is a solution. Namely a solution that looks like this here. Okay, then an initial condition to this other DAE. So here this transformed DAE, it has an initial condition, and the question is now when this is consistent. And it's consistent, well, if it's consistent with the actual solution. We know what the actual solution looks like. We can write this down. So we know that this actual solution, as we had it before, is this particular has this k equals 0 to nu minus 1 and to the k f to the kth derivative, and it's consistent if this if at t equal t0, this equation holds as well. So x of t0 should be this at t0, and then this should be the same as the x tilde to 0. Meaning, given a general initial condition, if we apply the q to the minus 1 to that, we get the initial condition for the transformed system, and then we can check this part, whether this is consistent with this part of the right hand side. So this we will also write it f tilde 1 f tilde 2. Here f tilde. Yeah, this gives immediate formula when is an initial condition consistent. And I have to know that this is CP, the initial condition of the reformulated. So here's the initial condition here. And it's consistent if this is true, and on the other hand, if we don't know anything about initial value, then from here we can see there is a consistent initial value. Just given the f, we can choose the value of all this at t equal to 0 and take this as the initial value for here. And then we have an initial value to the problem. And then we translate this back and saying that every initial value problem plus of the initial condition. So this is the actual DAE, ex dot x t0. So every such initial value problem with a consistent, very important initial value is uniquely solvable. And that's the theory. No need to prove here because we did all this hack before. Now, as I promised, to get back to does this mean in the other direction? So what if E and A is not regular? Well, here things are not so clear. Well, we know EA regular, then there is a unique solution, blah blah blah. But what's like the negation, or what do you say? The negative of this statement. The actual statement is EA regular, then this DAE together with an initial value has a unique solution, and then a negation can be like denying anything of that. So maybe it has not a solution. Maybe it has many solutions. So, oh no, that's here. So first thing is there is not a solution at all, but it also can mean that there is no unique solution. So whenever we can like negate one of these claims that there is a solution or that the solution is unique, then, well, we have, so to say, speaking out against, well, then that's a negation of this statement. There's a theorem for that, which we won't prove. I'll give you the reference in a second. But the main point is that if we have lambda EA, such a matrix pair, which is now in m times n, so different numbers of rows than of columns, still we consider the DAE that is associated with that if like there is a if this is not full rank, so if the rank is less than the n for all lambda, then one can show that this problem ex dot is ax and in a 0 initial value, which is often called the homogeneous problem. The homogeneous problem has a non-trivial solution. Non-trivial solution means that x is not equal to 0. And that's really a problem because because if you start in the 0 and if the DAE, if there is nothing that changes the value, so well, you see you start in x 0, then you will have a 0 here actually all the time, so there's no f that might change the values. So you would really want to have just a 0 solution here. But it can happen that you don't have only the 0 solution, but there can be x that are not 0 and that solve this problem. And this is well, a problem with this. So there won't be a unique solution because, well, this non-trivial solution you can add to any other solution and you will still have a solution. So this means there's not this unique solution. The other issue, like that there won't be any solution at all, this can happen if if the rank is full. So you have at much so you have full rank with respect to the columns. So you have n unknowns and the rank is you have full rank with respect to that. And you have is larger than n, meaning you have more equations than you have unknowns. then we will find an f which is sufficiently smooth, so that's not a problem here. So it will be a suitable f, but you won't find a solution to that. So you won't find an x such that ex dot is ax plus f. And then that's this problem here. So it does not have a solution. One problem is it might not be unique, and here that's like a contradiction to the assumption that there is at least one solution. Proof, as I said, is, you can look this up in the book by Kunkel and Merman. I just want to have an example here to tell you here we have we see both problems that I mentioned before. But well, see you on Friday, and then we go quickly through that, and I look forward to also having a look at the other exercises. Bye.